Hi, welcome to Math 4 Honors. I'm Kirk Weiler, and today we're going to be talking about continuous growth and the number e. Alright, so you should have had some exposure to the number e, the natural logarithm space, before, including in this course. But the idea of continuous growth, that's a little bit different. And so we're going to be looking at that today and kind of understanding what it means when we're told that we have continuous growth. But let's start with a review problem from the last lesson. Exercise 1 tells us that we have a population of bacteria that's growing at a rate of 6.5% per day, and it has some initial population p sub 0. Letter A asks us to write an equation for the population of bacteria as a function of the number of days since the population was at p sub 0. Pause the video for a moment and write that exponential equation. Do you have it? Alright, we're going to start some inking. Let's do it. So what we should know is that when we have an exponential function, right, p of t, we always have our y-intercept, our starting value, as our multiplier, as our original value, and then we get to multiply by 1.065 for every day that passes. So if t is the number of days, that really represents how many times we've gotten to multiply by 1.065. Now, bridging the gap, right, is letter B. Letter B then asks us, well, alright, if we're growing at 6.5% per day, which all that means is sort of at the end of the day, we could figure out, what our population is by multiplying what we had at the beginning by 1.065. Now the question is, what is the percent growth of the population per week and per hour, right? So again, it's, well, if I had some population at the beginning of the week, what would I have to multiply by to get the population at the end of the week? And likewise, per hour. So think about this in the context of the last lesson where we did a lot of work with percent. Pause the video now to see what you get. Alright, well, think about this, right? After 1 week, what we're really doing is we're looking at the population at 7 days, right? So that's going to be p sub 0 times 1.065 to the 7th. Now, ironically, I don't really care what the population is. I only care what I'm multiplying by. So if I take 1.065 and raise it to the 7th, I find I have 1.55398, etc. It's not the nicest thing. But now by looking at this, because I got to multiply by 1.55398, I know that it must have grown by 55.4% per week. Now, if you haven't already thought about how to figure it out per hour, pause the video now and consider it for a little bit. Alright, let's take a look. So, in terms of 1 hour, we have to think about what is 1 hour compared to a day. 1 hour is 1/24th of a day, right? There are 24 hours in a day. So this is really this idea of kind of going backwards, right? So if I raise the 1.065 to the 1/24th, what I find out is that every 1/24th of a day, oh, this is a small number, I get to multiply by 1.0026. That tells me that per hour, I'm growing at a 0.3% rate. Not a 3% rate, a 0.3%. Alright, so that's just some really review from previous work. Alright, now the number e, right? Hopefully it's something that you've been exposed to before. Let's talk about it a little bit. E is simply a number like pi. It's irrational. It's kind of obnoxious. It's 2.71 ... It goes on forever without repeating. It's given the letter E because it was named after the Swiss mathematician Leonhard Euler, one of the greatest mathematicians of all time. Leonhard Euler. Alright, so he called it E after himself. And it is used often when we want to look at what's called continuous growth, growth that is always happening. It's not like it grows a little bit and then it stops, it grows a little bit and it stops, right? And very often what happens is that what we do is we take a model that would be normally written as y equals a times b to the t, and we write it as y equals a times e to the kt. Right? Now, obviously, by sort of looking at these two equations, you can tell that the a's are the same, right? So it must be that if you think about this guy, let me pull it out here. We have a times e to the k, all raised to the t. That means that e to the k is equal to b. Man, there's a lot of letters here. There's a's, b's, t's, k's, e's. Keep in mind, e's a number. Keep in mind that t is time. So in each exponential model, you actually only have two what are known as parameters, two constants. The initial value, that's the same in both cases, that's the a, and then what you're multiplying by. When you write an exponential model in this form, what you're multiplying by is b. When you multiply, in this case, what you're multiplying by is e to the k. Same thing. The cool thing about this, then, is that we can actually determine whether the exponential model is increasing or decreasing based on the value of k. Alright? So if k is negative, then it is a decreasing exponential. And if k is positive, it's an increasing exponential. You can really think about this in terms of b, right? We always knew if the base was greater than 1, it would be increasing, and if the base was between 0 and 1, it would be decreasing. But again, think about it, right? This e to the k is equal to b. So if b is bigger than 1, k has got to be greater than 0, right? If k is any positive number, e to the k is going to be greater than 1. On the other hand, as soon as k becomes negative, let's just think about k equals negative 1, then I'd have 1 over e, and that would be a number that's between 0 and 1. The value of k is given a very special name. It's called the continuous growth rate, and it's always the percent in decimal form. Oh boy, that sounded confusing even after I said it. Let's take a look at exercise 2. Exercise 2 says the area of an oil spill is increasing at a continuous growth rate. This is amazingly important, this piece of terminology. A continuous growth rate. All right. As soon as we see continuous, that means we're going with this kind of model. All right, of 3.6% per hour since it first reached a size of 30 square meters. We want to write an exponential model for the area of the spill. Well, the way that we do this is that a, that initial value, is still going to be what we initially have. The big difference is now the model is very easy to write. The area is going to be 30 times e to the 0.036t. Notice, not 1.036, 0.036, right? That's it. That's the whole model. It's really kind of nice. A equals 30 times 0.036 to the t. All right, the key is that piece of terminology. Continuous growth! Exclamation points. Now, what's interesting is that, almost ironically, the fact that they say that it's growing at a rate of 3.6% per hour continuously doesn't actually mean that after 1 hour you've multiplied by 1.036. That's the weird thing. It doesn't actually mean that. Let's take a look at what actual percent the spill increases by in an hour, right? Well, one way to do this is to think about what we would have as a of 1. What is the area after 1 hour? Well, it would be 30 times e to the 0.036 times 1. Now, I could actually go on and calculate the area right now. I could do this calculation. But what I'm really interested in is just the multiplier. I just want to know, what did I get to multiply 30 by? So if I take my calculator out and I plug in e raised to the 0.036, I'll find that I get to multiply by 1.03665, etc. It's going to be ugly because he's an irrational number. Now, what's interesting, remember, is if I'm actually growing at 3.6% per hour, I should be multiplying by 1.036. But I'm not. I'm multiplying by something a little bit bigger. And in fact, the nearest tenth we can say that we're growing at 3.7% per hour. Very strange. We'll talk about this more tomorrow, in the next lesson when we talk about nominal growth rates versus effective growth rates. Nominally, in name only, we're growing at 3.6% per hour, but effectively, we're actually growing at 3.7%. The letter B also asks us, but by what percent does the area of the spill increase over 5 hours? Why don't you pause the video right now and try to figure that out. What does it grow by over 5 hours? All right, hopefully you found an answer of 19.7%. But let's take a look. We're going to use exactly the same type of reasoning. We're going to substitute 5 in. Now again, I don't actually care about what the area is. It's one of the really weird things in these problems. What I care about is what I got to multiply by after 5 hours. So if I put this into my calculator, and again, calculator use, you might have something like this, e raised to the 0.036 times 5, right? And that would give me 30 times 1.197217, etc. The point is, after 5 hours, I get to multiply by 1.197. So I get 19.7%. Again, what's rather odd is one would think that if you're growing at 3.6% per hour, then you just might multiply that by 5, and you'd get a nice even 18%. Notice we actually get more. Right? We've seen this before. This is this weird idea that, oh, we can just sort of add 5 3.6s together. All right. Now this is again a little weird, and it's, I have to admit, somewhat semantical. And what I mean by that is that if I tell you that an oil spill is growing at a rate of 3.6% per hour, not a continuous rate, but a rate of 3.6% per hour, then you should tell me that I'm multiplying by 1.036 every hour. If I tell you it's growing at a continuous rate of 3.6% per hour, then I'm multiplying by e raised to the 0.036. It's remarkable how close they are, right? I'm actually, when I multiply by e to the 0.036, I'm actually multiplying by 3.7%. All right, let's look at a situation that's decreasing. I think modeling using e is amazingly helpful, especially in a decay scenario. So let's take a look at number 3. The amount of a radioactive substance can be modeled with the equation A equals A sub 0 times e to the negative 0.042t, where t represents the number of years since it first started to decay, and A sub 0 represents the original amount of the substance present. What is the continuous growth rate as a percent? If you think you know the answer, pause the video for a second, write it down. Alright, this is really odd, but literally the continuous growth rate, I lost my pen. The continuous growth rate is always this number. So it's negative 4.2%. The great thing is that, of course, if you've got a negative growth rate, continuous or not, what it means is that your amount of substance or population or whatever is going down, right? It's decreasing continuously at negative 4.2% per year. Now, letter B is kind of interesting. It says, by investigating tables on your calculator, determine the half-life of this substance to the nearest tenth of a year. The half-life is defined as the number of years needed to reduce the amount of radioactive decay of the substance to half its original value. Now, what's weird is we don't really know what the original value is, right? So what we really want to know is how many years will it take for the multiplier to be equal to 1/2 or 0.5, right? That's what I want to know. So what I'm going to do is I'm going to take my graphing calculator. Let me open up my TI-84. Where did my screen go? It takes a little bit. I should have had this open up beforehand. Please excuse the pause. Here comes my calculator. of this, get rid of this, and let's bring the calculator in so you can actually see it. Alright, let me go into my y equals. Let me clear out anything I don't need, which is everything. Let me go into y1 and let's put this in. Let's put in e raised to the, I gotta grab my negative button, I can't even see it on my calculator. E to the negative 0.042 x. So I'm not going to even put in an initial amount because I really can't. Now what I'm going to do is I'm going to go into my table. I'll start my table at 0, but I think I'll probably make my years go by 1. And let's take a look at our table. Alright, so what am I looking for? Right, and here are my years. Here is what I get to multiply by after all those years. I'm looking for the half-life. Oh, wait, oh, almost had it. It's between 16 and 17 years, right? You see that at 16 we're multiplying by 0.51, at 17 by 0.489. This is when I'm going to go in, and I'm going to now start my table at 16, and I'm going to make my table go by tenths of a year. Let's take a look now. What do we have? There we go. I think 16.5. We could go a little bit further just to make sure it's closer to 16.5 than 16.6, but 0.5007, sorry, is closer to 0.5 than 0.4978. So based on all of this table data, right, we can now say that the half-life is 16.5 years. Eventually we'll be solving for the half-life exactly using logarithms and other tools, but that's a good way to do it by right now. It says, what percentage of the original substance remains after 2 half-lives have passed? Verify by examining the table. We looked at this question in a previous lesson, so you probably have a very, very good sense of it, right? But we can verify it now, right? What percentage of the original substance remains after 2 half-lives have passed? Well, after 1 half-life has passed, we've multiplied by 1/2, right? After another half-life has passed, we've multiplied by 1/2 squared, or 1/4. Remember, we're always modeling the percent that remains, not the percent that's left, so 25%. If we actually take a look at this on the calculator, it's kind of rather cool. I can go back into my table, right? Think about, we've got 16 and a half years for a half-life. So 16 and a half times 2 would be 33. Why don't we start at 32? Why don't we go by ones? And let's take a look at our table. And there it is. Look at that. At 33 years, we're just about at a quarter. Isn't that nice? Alright. Let's take a look at number 4. Number 4 asks, which would have the greater annual percent growth? A population that grows at 0.58% per month, or a population that grows at a continuous rate of 7% per year? So in this case, what we always want to be able to do is compare apples to apples. We want to be able to say, okay, look, what I really want to know in both cases is, what do I get to multiply by after a year? What is the actual effective growth rate after a year? So pause the video if you think you know how to find that for both of these two scenarios, and then we'll go through which one is growing faster. It's very close, by the way. Alright, let's take a look. Let's talk about growing at 0.58% per month. Notice in this case, they never say it's continuous. So we're going to just do our typical, I multiply by 1.0058. That's tricky. It'd be tempting to do a 1.058, but that would be 5.8%. Now, if I want to know what I get to multiply by after a year, I'll raise that to the 12th, right? That'll give me 1.00. Oh, no, sorry. Let me get rid of that second 0. That would give me 1.07186, etc. So I don't know how accurate I need to be, but let's go with 7.19% per year. That's my actual yearly growth rate. Whoops. That almost looks like the word actually, but not really. All right, here in this problem, they tell me I have a continuous rate. Right, in this case, what I'm getting to do is I'm getting to multiply by e to the 0.07 for every year that goes by. But I'm only talking about 1 year, so I'm just going to raise e to the 0.07 power. That's what I'd get to multiply by, and it would be 1.0725, etc. And that would be, let's say, 7.25% per year. Right? And that's also an actual growth rate. In other words, that's what we get to multiply by. So clearly, this has the greater rate. Right? We're now comparing apples to apples. Right? Okay, let's take a look at the last exercise. In number 5, Mr. Weiler, gosh, where did I come up with that name? Mr. Weiler needs a sustained caffeine level in his blood of at least 45 milligrams, or he gets very irate. This is a very realistic problem. Caffeine is metabolized or used up by the body at a continuous rate, that's the key, of 17% per hour. It's being used up by a continuous rate of 17% per hour. Used up. Graphically determine how many hours to the nearest tenth it will take after having a cup of coffee with 150 milligrams of caffeine for him to become irate. All right. Let's model the amount of caffeine Mr. Weiler has in his bloodstream, that would be me, let's call it C of t, as a function of the number of hours. Now, we know that we're going to have a model that looks like this because it says continuous growth rate. A stands for the amount of caffeine we have in there originally, that's going to be 150 milligrams. Now, this is tricky. We're using it up, which means it's a decrease. It's negative 0.17. Negative 0.17 times t. All right. Now, if I want to figure out the solution to this equation, right, because that's what I really want to know, this is the I rate level. Eventually, again, we'll solve this algebraically using logarithms. But for right now, we're going to solve it graphically. And it's going to be simple, right? We'll just come over to our TI-84. We'll go into y equals. In y1, we'll clear this thing out, and we'll go with 150 times e raised to the, sorry, I gotta grab my negative button, e raised to the negative 0.17x. Alright, so there's my caffeine level, and I want to know when it hits 45. Now, it's kind of tricky because, again, I don't exactly know the best window. You know, maybe what I want to do is maybe look at the table, and I can kind of tabularly see. So here's my caffeine level. Here's that constant 45. We're watching for it. Oh, look at that right there, right? It goes from 45.6 down to 38.5 roughly. So it's around 7 hours. But, you know, more than anything, what this does is it gives me a good window. Let's go into my window now. Let's go 0. Looked like I was going to hit it. Oops, before 10. Let's try that. 0. 10. I don't think I really need any negatives. I'll go 0. What did I start with? I started with 150, maybe go 160. Now let's graph. There's my decreasing exponential. Here's my linear. I can now ask my calculator to calculate my intersection point. That's option 5. Asks me for my first curve, my second curve, and my guess. And what I find, right, maybe just do a little sketch of this graph. Right, caffeine versus time. Looks like this here, and that occurred at 7.1. Doesn't really matter, and of course I know that it occurred at 45. But yeah, at 7.1 hours, I'm going to start getting irate, and that's about right. If I don't have a cup of coffee after 7 hours, that's going to be a problem. Speaking of which, I think I need one now. Anyway, thank you so much for joining me again for this lesson. Until next time, keep solving problems and keep thinking hard. Take care.